This is video lesson number 3 for level 2. We're looking at chapter 2, section 2 again. Today we're just going to be talking about biconditionals and good definitions. We'll start off with this definition. Perpendicular lines. Two lines that intersect to form right angles. Well, this can be written as a conditional statement, as almost all definitions can. If two lines are perpendicular, the condition, defined then, they intersect to form right angles. Now, we know this to be a true statement because this is what the definition says. However, the converse says, if two lines intersect to form right angles, then they are perpendicular. Ignore the extra comma. If two lines intersect to form right angles, then they are perpendicular. These two conditionals are both true, thus forming a biconditional. The previous lesson we looked at biconditionals in order to set this up, that definitions in geometry need to be biconditional. Theorems and other things that we discover do not, but definitions need to be biconditional. Otherwise, they are not well-written definitions. Here are the characteristics for a good definition. 1, it must use clearly defined terms. We do not want things that people have never heard of or terms that are more advanced than the word you're trying to define. 2, they are precise. They avoid vague words such as it is large or it's sort of. Things that do not directly say what it is very precisely, we do not use in a good definition. And lastly, and most importantly, it must be reversible to be a good definition. This is difficult. Sometimes that's not going to be able to be done, but to be a truly good definition, a precise definition, it will be reversible. Here's the definition. Perpendicular lines, two lines intersect to form right angles. As we said earlier, this is biconditional. Two lines are perpendicular if and only if they intersect to form right angles. That biconditional is critical to us calling it a good definition. And it reminds us how we write our biconditionals with if and only if. Okay, is this a good definition? Complementary angles are two angles, the sum of whose measures is 90 degrees. Well, is it clear? Yeah, very clear. Two angles, and they need to add up to 90. It's precise, because 90 degrees. That's an exact measurement that it must be. And it's definitely reversible, because we could say two angles are complementary if and only if the sum of their measures is 90 degrees. Now, notice it doesn't say anything about they have to be adjacent or they have to not be adjacent or coplanar or any of those extra things because they are not needed. You don't put extra material into a good definition. We have to be precise. Is this a good definition? A square is a figure with four right angles. All squares have four right angles, so it seems to be a good start. But the answer is no. This is not a good definition. It's relatively clear. Square, four right angles, nothing confusing there. It's precise, it's short, it's to the point, but it's definitely not reversible. Okay? And in terms of precision, we know that a square has more than just four right angles. So we're not talking about precisely what a square is. If a figure is a square, then it has four right angles. This is true. If a figure has four right angles, then it is a square. This is false. The first statement true, the converse is false. This means it fails to be reversible. Rectangles have 4 right angles and do not have to be squares. Here is a rectangle. This is not a square. Not all 4 sides are congruent. We have 1, 2, 3, 4 right angles meeting the condition that we thought if a figure has 4 right angles would make it a square. But it's not. This is not a good definition. That ends level 2's lesson number 3. It was a short lesson. Most of the work in this level or this assignment will involve conditionals, converses, biconditionals, and definitions, putting it all together.